So in this video we are going to talk about the simplest use of the simulation, any simulation or Aspen-Huygens simulation, which is extracting the physical properties. So this is the simplest. So if we are opening the water over here and we have created this stream, the composition is 100% water, the conditions is it's always liquid and it's at a temperature 25. So in this case I'm going to remove this. It is not 100% liquid or 100% vapor. I'm looking for a pressure which is atmospheric pressure. So 101, this is the atmospheric pressure. So at the atmospheric pressure and this temperature, we know that the water will be in the liquid phase. That's why we have a vapor fraction here equal to 0. We don't have any vapor at this temperature. Okay, so after the condition from the worksheet, you'll find out that you have the properties. So this section is actually the simplest use of Aspen-Huygens. After adding the condition, you can go to the properties over here and extract any information that you want to know. Like if we want to know about, so here this is the molecular weight. We know that the water is H2O, so 16 for oxygen and 2 for hydrogen, so it's 18. So this is the molecular weight of water. And instead of doing the calculation, you can do so, extract this information from Aspen-Huygens for the molar density and the mass density. So we know that the density of water at the normal conditions like the room temperature and the pressure, it's 1000 kilogram per meter cube. Also some people know it in the pound per cubic feet, which is 62. Okay, so you can extract all the information that you need from the, like if you want to know the specific heat at constant volume, any information that you need to know will be available here in the section properties. If you are looking for a specific property and it is not available here, you can add it. So this first section, you can view all the correlation set list. Okay, the second section here, this is really important, which is related to adding a new correlation. So if the information I'm looking for the water is not available here, I can go over here and look for the information that I want to add. Like if I okay, so it will make more sense because here all the information for water is displayed for something like the natural gas. For the natural gas at this temperature and this pressure, so the natural gas here we have the condition. Here the properties also is displayed. So the molecular weight is 17, the mass density is 0.7, this is extremely low, and because the density of the gas is always less than the density of the liquid, maybe at the same conditions. So the property correlation control we are going to add here. What we are dealing with here is gas. So here we are looking for the information related to the gas that is not displayed here. So here if I'm going to add the water dew point, if this composition has water and we are looking for the water dew point, so I'm going to apply this one and look here, we will find out it is added here, but the information is not displayed because we didn't have water in the composition. So if I'm going to add another one, and here we are dealing with a gas, so go to the gas over here and we look for the mass density at standard condition. A standard condition is 60 degrees Fahrenheit and 1 atmosphere. Okay, so we are applying this one. I'm closing here and going back. It will be displayed at the bottom. So the mass density at the standard conditions will be 0.73 kilogram per meter cube. Okay, so if you are having another property that you need to add, you can add it from here. This one is for the arrangement from the top to the bottom and bottom to the top, and here we are going to save and search. For the composition here, we know that we have already entered this one. This one we enter at the beginning. So this is like the stream definition. So the composition and the conditions, we enter these two at the beginning. After that, we go to the properties where all the data will be printed. Okay, so this is for the properties section. here if we enter, so this section will be covered more in the refinery. For the attachment over here, we have a unit operation and the analysis. For the unit operation, this material stream is not attached yet with any valve or compressor. This is what is meant by unit operation. It will be an inlet for someone and an exit for someone. Okay, and this is the most advanced. It's a PF or the dynamic. Okay, so this is for our natural gas. Before, I've talked a lot about doing a stream analysis, especially talking about the phase envelope. The phase envelope is a relation between the pressure and temperature. This is the most common relation between pressure and the temperature, and you know at a specific pressure and a specific temperature what will be the phase. The phase is important because if we are dealing let me open F4, click F4 and have our model palette. If we are dealing with a liquid, we need to use a pump. If we are dealing with a gas, we need to deal with a compressor. So how we make sure that we are dealing with a liquid? We know that from the vapor fraction. If the vapor fraction is 0, we can use a pump. If the vapor fraction is 1, we can use a compressor. We can't use a mixture of feed for the compressor or a liquid. That's why we usually use a separator for this unit to make sure we are using 100% vapor for the compressor and 100% liquid for the compressor. Otherwise, you will have a mechanical problems and also a troubleshooting. Okay, so that's why it's important to have a stream analysis called a phase envelope. So it shows you where exactly you are. So without, okay, if we are opening this again, without entering our phase envelope, we know that this is 100% vapor and this could be fed to our compressor. Okay, if I want to know more about the conditions like the temperature and the pressure where our stream will be vapor, we can create a phase envelope. So here at the attachment, we have a unit operation. We have talked about this before. It's related to what is the unit operation that natural gas feed stream is attached to. For the analysis here, we can create. So here we can attach any stream analysis. So we are going to create. These are the options available. So we have boiling point curve, carbon dioxide freezing out, critical properties, and this one is the phase envelope that I'm looking for. So here we don't have a mercury, so we can't have a free mercury calculation. The hydrate forms when we have water. So in this case, our material stream doesn't have water. So it doesn't make sense that we do a hydrate calculation for a stream that actually doesn't have water. But in real time plant, the natural gas usually has water. Okay, for there will be other analysis here, but now we are looking for a phase envelope. Okay, so I'm going to add this one. After pressing it, we will have this envelope information for the natural gas. Okay, so for the 2-phase critical temperature, and here we have 3-phase. The difference here, if we have water in the stream, it will form a 3 phases: a gas, a liquid of hydrocarbons, and water. If we are having with only hydrocarbons, these hydrocarbons can be a vapor or a gas. Okay, so here we have a 2-phase critical temperature and critical pressure. Okay, for this definition, this is really important, and it's important also to see the envelope. So let's talk about it in our next video.